Hello. What we're going to be talking about in this video is something called partitioning variance. Partitioning variance is one of the most important fundamental concepts in statistics, and if you want to understand how things like analysis of variance or linear regression work, then you need to understand what we're talking about when we're talking about partitioning variance. So let's start by generating some example data. Here's some code from R that I use to generate two variables, variable 1 and variable 2, and there's some points that we need to make before we go on to look at how these variables are distributed. First of all, we've got a grouping factor. So each of these variables can be grouped into three separate factor levels, A, B and C. Secondly, variable 1 is drawn from distributions with all of the means being equal to 20. So each group within variable 1 should have a mean that's somewhere close to 20. Variable 2, on the other hand, is drawn from three different distributions. So factor level A in variable 2 is drawn from a distribution with a mean of 15, factor level B is drawn from one with a mean of 20, and factor level C is drawn from one with a mean of 23. So the means of each group within variable 2 should be different and should be close to those values for the distributions that we've drawn them from. So the means of the groups are different in variable 2, but not in variable 1. The other point to notice is that all of these data are drawn from distributions with the same standard deviation and therefore the same variance. So each group in our two variables is drawn from a distribution with a standard deviation of 3. Okay, let's visualize these data and have a look at what they look like. So these are frequency densities, which are just rather prettier frequency histograms really, of our two variables, with variable 1 at the top and variable 2 at the bottom. And just looking at these, you can see that the amount of spread in variable 1, the amount of dispersion in the data, is less than the amount of dispersion in variable 2. So if you consider all of the data put together, we're not thinking about individual groups, we're just thinking about the whole of the data in variable 1 or variable 2, then variable 1 has a range which is about 10 to 30, but variable 2 has a range which is about 5 to 35. And as I'm sure you remember, all the groups in variable 1 are drawn from distributions with a mean of 20, but the groups in variable 2 are drawn from distributions with means ranging from 15 to 23. So when the means are different, there's more dispersion in the overall data set. And we can make that point even more clearly by calculating the variance for each variable. So the variance for variable 1 is 8.69, but the variance for variable 2 is 20.68. So the overall variance for these variables is very, very different. And that difference is a consequence of the fact that there's big differences between the means in variable 2, but not variable 1. So part of the variance in variable 2 has arisen as a consequence of the variance within each group, what we call the within group variance, but part of it has arisen as a consequence of what we call the between group variance. So we have variance arising because of the differences between the groups, but we also have variance arising because of the variance that's already there within the groups. Let's just try and make that a bit clearer. So here's variable 2 again. Here are the centres of the three distributions of the three groups within variable 2, and you can see that those are positioned in different places on the x-axis of our graph here. So those differences between the groups are contributing a certain amount to the variance of the overall variable, and then we also have variance within each group. So that variance that we can't actually explain, because the only thing we know about these data is that they come in three groups, so we can't explain any of the variance within the group. So that's called the error variance, or the residual variance, or the within group variance. That contributes a part of the variance, and then the between group variance, otherwise known as the treatment or the factor variance, contributes the rest of the total variance of variable 2. Okay, how do we separate out the treatment variance from the error variance, or the between group variance from the within group variance? Well, we don't actually calculate variances immediately. What we calculate is something called the sums of squares for these different components of the variance. And we calculate the sums of squares because they add up together. We would say they are additive, whereas you can't do that with variances when you calculate them. Here's a formula that you might recognize. This is the formula for the sample variance. So the sample variance is calculated by calculating the mean, subtracting the mean for each data point, squaring the difference between each data point and the mean, adding them all up, and then dividing by n-1, which is the degrees of freedom. If we want to know the sum of squares for the entire variable, that's the total sum of squares, we calculate it in a very similar way to the variance. We just don't divide by the degrees of freedom. So for each data point, we subtract the mean of the total variable. We then square that difference, and then we add all of those differences together. So that's the total sum of squares. If we want to calculate the error sum of squares, so that's the within group sum of squares, we do the same thing, but we do it separately for each group. So for group A, we calculate a mean, we subtract that mean from each data point in group A, we square the result and we add them together, and then we do the same for group B, and then we do the same for group C. And if we want to calculate the treatment sum of squares, the between group sum of squares, that's simply the total sum of squares minus the error sum of squares. We can calculate it in a different way if we want, but the easy way to work it out is to just subtract the error sum of squares from the total sum of squares. Let's try and see that using another example. I've got a rather smaller data set here, but we've got three groups again, and each group is drawn from a distribution with a different mean. So we've got group A in the brown, we've got group B in the, I believe that colour is aquamarine 4, and then we've got group C with red points on this graph. So if we want to calculate the total sum of squares, we need to calculate the overall mean for all of the data put together. And in that case, that overall mean is 19.0. We can draw it in on this graph like that. So that horizontal line represents the grand mean, as we would call it, of the total variable. And then for each data point, we can calculate the difference between that data point and the grand mean. So this data point here has a value of 13.04. So in order to calculate the total sum of the squares for this variable, we would subtract the mean from 13.04, and then we would square the result of that. So if we do that calculation, it's minus 5.96 squared, which is equal to 35.5. And then we would do that for every data point in this data set and add them all together, and that gives us the total sum of squares for this particular variable. Don't forget, our variable is in three groups, so we can also calculate an error sum of squares by calculating the mean for each group separately. So group A has a mean of 20.3, group B has a mean of 15.2, and group C has a mean of 21.4. We can draw those means in, there we are, and then we can calculate a sum of squares for each group and then add those together to give us the error sum of squares. So going back to our data point with a value of 13.04, the mean for that group is 15.2, so our calculation is now 13.04 minus 15.2 squared, and if we work that out, it's minus 2.16 squared, which is 4.67. So for that particular data point, its contribution to the error sum of squares is 4.67, and we would then do that for every data point in our variable once again. And then we can calculate our error sum of squares by adding together the sum of squares for group A, the sum of squares for group B, and the sum of squares for group C. So we can generate our total sum of squares and our error sum of squares like that. If we want to calculate our treatment sum of squares independently, we can do that. And the treatment sum of squares is simply the difference between the group means and the grand mean for each data point squared added together. So if we go back to that data point there, the group mean is 15.2, the grand mean is 19. So for that particular data point, its contribution to the treatment sum of squares is minus 3.8 squared, which is equal to 14.44. And we would do that for every data point in our variable again to give us the treatment sum of squares, or we can just calculate the treatment sum of squares by subtracting the error sum of squares from the total sum of squares. So here's some R code that will actually do these calculations for us if we want to. First of all, we're calculating the means for each group with that bit of code there. We then calculate the grand mean, and then we've got the total sum of squares, which is the sum of all the data points minus the grand mean squared. We've got the error sum of squares, which is a similar calculation but done for each group individually and then added together. And then we've got the treatment sum of squares, which in this case we've calculated by subtracting the grand mean from the group mean for each group and calculating the sum of squares that way. And if we ask what those are, these are our values. The total sum of squares for this particular variable is 309. The error sum of squares is 134.7. The treatment sum of squares is 174.6 or 0.7 if you round it properly. And if you add those together just to check, you can see that the sum of those is equal to the total sum of squares. So let's just summarize what we've seen so far. When we have a variable with data that we can separate into groups, the total variance of that variable has two components to it. So there is the between group variance, the variance that arises from the differences between the means of each group, and then we have the within group variance, which is the variance that arises from the amount of dispersion of the data within each group in our variable. The between group variance is not usually actually called the between group variance. People usually call it something like the treatment or the factor variance, depending on the kind of analysis that you're doing. And the within group variance is usually called something like the error variance or the residual variance. We can partition the variance by calculating the within and the between group variances, and that partitioning of variance is the really fundamental thing in a lot of these analyses that we're going to be looking at. We partition the variance by calculating the sums of squares for the total and the error and the treatment. And in fact, we only need to calculate two of these because they add together. So if we know the error and the total sum of squares, we can calculate the treatment sum of squares very easily. If we know the total and the treatment sum of squares, we can calculate the error sum of squares very easily. We've mentioned that partitioning variance is important in a lot of different analyses. Probably the single most important technique in statistics is the general linear model. Things like linear regression and analysis of variance are just components of the general linear model, and partitioning variance is the most important foundation of the general linear model. So if we're going to understand the general linear model, we need to understand partitioning variance. So far, I've told you how to partition variance, but we've not looked at what you can do with your error and your treatment sum of squares once you've actually calculated them. What we're going to do in the next video is we're going to look at how we can use these values that we've calculated to construct an ANOVA table, an analysis of variance table, and do some statistical testing on whether or not we have significant differences between the means in our grouped variable.